All right, we'll get started today, and the only thing I'll announce before we start today is just the first reminder or notification about next week's Exam 3 review. So the last part of the course always seems to move pretty fast, and we're already coming up close to another exam review. It'll be a week from tomorrow, so that'll be April 22nd, and that's always the same place, same time. So 2 p.m. in SEC 102, and I plan to get the file posted for that tomorrow at the latest. So you'll have that available. That'll be Exam 3 review, and then as I mentioned, and I'll have more details about next week, the plan is the final exam review will be divided up into 3 sessions, 2 of them in class, 1 of them the following Friday, April 29th. So we'll have that coming as well. But for now, the main focus, of course, is the upcoming Exam 3, and what the plan is for today is to finish all the material that will be on Exam 3. So that's going to be through 9.4. So if you follow along with your textbook, and you'll notice in Blackboard we indicated that pretty clearly, section 9.4 is the last section that will be covered on the third midterm. The rest of Chapter 9 will not be until the final exam, so roughly half and half, split up that way. All right, so we're going to talk today more about vapor pressure and phase changes. So we introduced last time what vapor pressure is. Vapor pressure is the idea that when you have a liquid, some portion of the molecules have enough kinetic energy to escape the surface, and that creates a small pressure above that liquid. And the value of that pressure is, as we talked about last time, dependent on temperature. So we talked about how if you increase the temperature, you increase the vapor pressure. And there was a mathematical relationship for that we also introduced, which we'll use again one more time today. Now, the other factor that we should understand how it influences vapor pressure are the intermolecular forces, which is another important concept that we introduced as a key factor in what we're talking about in this chapter. So let's first talk about the relationship between IMFs and vapor pressure. Hopefully, with everything we've talked about now, this should be pretty intuitive for us, which is that if you have stronger intermolecular forces, so we learned how to rank intermolecular forces based on what type they are, and a little bit about also how the molecular structure and composition affects that. So the stronger intermolecular forces correlate with a lower vapor pressure. All right, so that should make sense to us because remember we said vapor pressure requires molecules to escape the surface of the liquid. If there's stronger forces holding them together, less of those molecules are going to escape the surface, therefore you'll have a lower pressure. All right, so there's sort of that inverse relationship between IMFs and vapor pressure. All right, and again, just to briefly state the reason why, it's because vapor pressure requires molecules to escape the surface, and less of those will do that if the IMFs are stronger. Okay. So a nonpolar substance which only has London dispersion forces would typically have higher vapor pressure than something that's polar or has hydrogen bonding like water. And then there's also a relationship between intermolecular forces and enthalpy of vaporization. So when we talk about vaporization of a substance going from the liquid phase to the gas phase, the enthalpy change associated with that, the amount of heat that we have to put in to cause that to happen, is also related to the intermolecular forces. And this one, again, should hopefully make intuitive sense, which is that this time they're directly related. So compounds that have stronger intermolecular forces tend to have larger enthalpies of vaporization. And again, there's a brief reason for this. This is because if you have stronger intermolecular forces, you need to put more energy in to break those intermolecular forces and vaporize the substance. Because whenever we're vaporizing something, we have to break free of those intermolecular forces that are holding it in the liquid phase. And so if those intermolecular forces are stronger, it requires us to put more heat in. So both of these should make pretty sense. And this is kind of the qualitative relationship between intermolecular forces and these two parameters. All right, so we're going to move on to now then is kind of linking a lot of these ideas together and talking a little bit more precisely now about phase changes, their definitions, and so on. All right, and so a lot of this will be kind of review, but we're going to basically make the definitions more rigorous than they have been. So we talked at the very beginning that boiling point is the temperature at which a liquid will convert to a gas. Now that's a very imprecise definition. The more appropriate definition now, with our knowledge about vapor pressure already having been sort of covered, is the temperature at which the vapor pressure equals the atmospheric pressure. So what that means is that the boiling point is dependent on what the atmospheric pressure is, because it's going to be whatever temperature that substance has a vapor pressure that reaches atmospheric pressure. Because again, the vapor pressure is temperature dependent, so it's wherever whatever temperature that occurs at. We already talked about the enthalpy associated with it, which is still just the enthalpy of vaporization, so that's a review. But that's going to be important for some other things we'll talk about today, because again, when we're trying to figure out how much energy or how much heat is required to vaporize a substance, this is going to be the term that determines that. And enthalpy of vaporization is usually going to be quoted per mole of substance. So it's usually going to be the amount of heat required to vaporize 1 mole of substance. And we'll see that again today in a slightly different context. Now the other phase changes we haven't talked as much about, but the other direction for liquids, so liquids can be vaporized into the gas phase, or they can be solidified. They can turn from liquid to solid if you cool the temperature, and we call that temperature the melting point. This one has kind of a weird definition, and it's not one that we usually think about in these terms, but this is the precise definition. So melting point is the temperature at which the vapor pressures of the solid and the liquid phases are equal. So in this case, it has nothing to do with the atmospheric pressure that's around the substance. It just depends on the vapor pressures of the solid and the liquid form of that substance, and when those two are equal, that's when you're at the melting point. But of course, from a practical sense, what the melting point refers to, again, is the temperature at which, if you have a solid and you warm it to that temperature, that's when it'll start to convert to a liquid. Or if you have a liquid and you cool it to that temperature, that's the point at which it will start to convert to a solid. So that's really, again, the more practical and easy definition. But in terms of vapor pressures, it has a definition that states that it's the temperature at which the vapor pressures of the solid and liquid phases are equal. But again, we don't need to use that definition too often. And as we said, every phase change has an associated enthalpy. And I don't think we talked about this one yet for freezing or melting. And this one is called the enthalpy of fusion, which will be abbreviated as delta H FUS for fusion. And this is the enthalpy change associated with the melting process. So it will also be a positive value because you have to put heat into the substance to melt it. So you're talking about that process when you're defining this enthalpy. So both phase changes that involve the liquid as a center point, going in either direction to gas or going in, to lower temperature to cooling to solid, they have precise definitions for those phase change temperatures, and they have associated enthalpy values. Now, when you quote the melting or the boiling point of a substance, so when we say the boiling point of water is 100 degrees Celsius, well, as we said above, the boiling point is dependent on the atmospheric pressure. So the standard value that you quote for a substance is called the normal melting point or the normal boiling point, and this is the temperature of the phase change when the surrounding pressure is 1 atmosphere. So when we say the boiling point of water is 100 degrees Celsius, that means it's 100 degrees Celsius when the atmospheric pressure is 1 atmosphere. Or similarly, the melting point of water being 0 degrees Celsius, that occurs again when the atmospheric pressure is 1 atmosphere. Melting points are not as dependent on pressure as boiling points are, but nonetheless, it's still defined as 1 atmosphere of surrounding pressure when we talk about the normal melting point or boiling point. All right. So what this means then, if we're talking about the normal boiling point of a substance, we said that boiling point is when the vapor pressure equals the atmospheric pressure. So at the normal boiling point, the atmospheric pressure is 1 atmosphere, which means this is the temperature at which the vapor pressure is also 1 atmosphere. All right. And so we had an equation that we introduced last time, which is states the temperature dependence of vapor pressure and involves the enthalpy of vaporization and some other terms. So in principle, you can calculate the boiling point for any substance if you know everything else, because it's just going to be the temperature at which vapor pressure equals 1 atmosphere. All right, and then at that point, you've reached the normal boiling point of the substance. So then let's use those concepts for a slightly different type of problem that involves the equation we introduced last time. All right. So it's going to end up being the same equation that we did, which is the temperature dependence of vapor pressure, but now we're going to use also the definition of normal boiling point as part of that. So let's say we have a liquid that has a vaporization enthalpy of 35.5 kilojoules per mole and a normal boiling point of 122 degrees Celsius. What would this boiling point be at the top of Pike's Peak, where the barometric pressure is 457 millimeters of mercury? So if you go to the top of the mountain, the pressure lowers. If you've been up there, you experience what that feels like. It's not always a great feeling. And so we're going to see how does the boiling point change then when you go to these lower pressure atmospheric conditions. So in this problem here, though, we're again thinking about the temperature dependence of vapor pressure. It may not be obvious here, but we're looking again for a boiling point, another temperature at which the vapor pressure is this value, because the boiling point is going to be the situation when the vapor pressure equals the surrounding atmospheric or barometric pressure. So this is going to be the equation we're using for this, which we introduced last time. So the natural log of the ratio of two vapor pressures is equal to the enthalpy of vaporization divided by R times 1 over T2 minus 1 over T1, where those are the two temperatures that are associated with each of the two vapor pressures you're comparing. So in this problem here, we know that P2 is going to be 457 millimeters of mercury. We're trying to find T2, the temperature at which the vapor pressure equals 457 millimeters, because that's going to give us then the boiling point at that pressure. But then what is the other two pressures and temperatures going to be, P1 and T1? Well, this is going to be our T1, which is the initial temperature, the boiling point at atmospheric pressure. And then when we say normal boiling point of 122 degrees Celsius, that means that's the temperature at which the initial pressure is equal to 1 atmosphere, or 760 torr. So in other words, if we give you the normal boiling point of a substance, that's going to be the temperature at which the vapor pressure equals 760 torr. So we have one set P1 and T1 together here from this information, and now we're trying to calculate the temperature at which the new vapor pressure would be 457 millimeters, which would be the atmospheric pressure at the top of a mountain like this. So now we can just start putting the numbers in. So the natural log of P1 we said is normal atmospheric pressure, 760, and we're trying to calculate at what temperature the vapor pressure equals 457 torr or millimeters of mercury. And then that's going to equal the enthalpy of vaporization over R. So we have to put this value into joules because the value of R is in joules. That's on our periodic table, but we have to convert this to joules. So it's going to be 35,500 joules per mole. And then divided by the other value of R, which is in joules, which is again on your periodic table, so you don't have to memorize it, but 8.314 joules per mole Kelvin. And then we're going to be solving for T2. And then T1 is the temperature associated with the vapor pressure being 760. That's going to be the normal boiling point of the substance, which is 122 Celsius, which is 395 Kelvin when we convert to Kelvin. So in these equations that involve absolute temperature, we do have to make sure everything is in Kelvin for this to work. All right, so those are going to be the numbers we put in. We just have to solve for T2. So here it's a little bit more numerical, I suppose. We don't have to use exponents in this case. So it's just going to be, if you take the natural log of that ratio, it comes out to 0.5086, and that equals those two numbers divided, which is 4269.9. I'm just going to put some of the intermediate algebra in here because it's a little bit different than we've done before. And then we distribute that, and that comes out to minus 10.81. And so when we solve for T2, we get 377 Kelvin, which is 104 degrees Celsius. All right, and it makes sense that it's lower because we're going to a place where the atmospheric pressure is lower, which means we'd have a lower vapor pressure to reach the boiling point, which requires a lower temperature than the normal boiling point. So this is, again, just another application of that relationship we learned last time, where we're using the definition of normal boiling point to say that this is the temperature at which the vapor pressure is 760. Now we're calculating it at a different pressure where the other temperature, T2, is our only unknown. Now what you'll see here, this is just something to think about a little bit in your everyday life. The temperature, the boiling point at the top of the mountain is lower. And so that would be true for water as well. So if you're boiling water here close to sea level, it's going to boil at basically 100 degrees Celsius because our atmospheric pressure is close to 1 atmosphere. But if you go to the top of a mountain, the boiling point of water goes down by a few degrees at least. So I don't know if they still do this anymore, but I remember when I was young, if I look at like the back of a food package where you have to boil something in water, like rice-a-roni or noodles, whatever the heck it is, it'll say if at high elevation boil for a few minutes longer, and that's why, because at the top of a mountain the boiling point of water is lower, or the boiling point of any substance will be lower, and so if you're boiling at a lower temperature, you have to cook it for a longer time to be fully cooked. So that's why that is there. So this shows how you can calculate that. If you know the two pressures you're dealing with and the normal boiling point, you can calculate the boiling temperature at any other pressure. Okay? So any questions on that? Okay, so what we're going to move into now is another one of the few sort of quantitative things we're going to talk about in this chapter. Most everything we're doing in chapter 9 is conceptual, as I said, and it's not going to require us to know a lot of depth, but it's still going to be several different things, and mostly, again, just concepts, not so much with numbers. Here's one of the few numerical things we'll do, which is what's called a heating curve. So what a heating curve is it allows us to determine the total amount of heat that's required when we want to raise the temperature of a substance, maybe do a phase change on that substance, or some combination of those two. So in chapter 7, we learned how to calculate the heat when we raise the temperature of a substance. That's just mc delta T. So now we're going to combine that with what we know now about phase changes to figure out what happens if we heat a substance and it also goes through a phase change as part of that process. So let's go through all the possible steps then that we can have. So let's say we start with ice, and we're just adding heat to the ice. We're just take a block of ice, put it on a stove. Now you guys know what's going to happen, right? So first, the ice is going to warm up a little bit, and then it's going to melt, and then it's going to warm up some more, and then it's going to get high enough to boil, and then it's all going to boil off. So that's basically what happens when we heat it. So it's going to go through a couple of phase changes, and the temperature is going to increase the whole time. So let's look at what that looks like sort of graphically. So what we're going to plot here is the temperature of the water, which starts out as ice, but of course can go through phase changes in degrees Celsius. And we're just, again, adding heat at a constant rate. Now, we're not going to really use these heating curves a lot, but I think they do help us understand a little bit about what's happening. And then once we go do the calculation for something like this, it'll make a little bit more sense. So let's start with ice that's at minus 20 degrees Celsius. So we know that the melting point of water is 0 degrees Celsius. So below 0 degrees Celsius is going to exist as solid ice. And so we can warm it up to 0 degrees Celsius, and it'll remain ice during that time. So this first phase here, it's always going to be ice. It's just solid water getting heated up from where it starts to the phase change temperature. Now, once we get to 0, we know that that's going to be the temperature at which the solid ice starts melting and converting into liquid water. And so at 0 degrees Celsius, we're going to remain at a constant temperature until all of the ice is converted into water. And basically the length of each segment is how much heat goes in. So I'm going to try to draw that a little bit to scale, but it's kind of hard to do exactly. But during the phase change process at 0 degrees Celsius, it's going to remain, is this going to let me draw or not? There we go. It's going to remain at a constant temperature until all of the ice is converted into water. So in this region here, we have a mixture of ice and water. Ice being solid water, water being what we call it typically when it's a liquid. So you're going to go through the phase change at 0 degrees Celsius until all of the ice is melted and converted into water. And then at that stage, once it's all 100% liquid water, then it's going to start warming up again as we add more heat to it. And that again would be another phase where we're just calculating using mc delta T. So it's going to exist as liquid water all the way up until the boiling point, which is 100 degrees Celsius. So as you add more heat to this liquid water, the temperature is going to warm up. And you're going to get to the boiling point, which is 100 degrees Celsius. So in this region here, we just have water, liquid water, being warmed up from 0 degrees Celsius where it's all melted up to 100 degrees Celsius where it'll start to boil. And then same thing, once we get to the next phase change temperature, which is the boiling point in this case, at that temperature we're going to boil all of the water, and it's going to convert into water vapor, which we also call steam, more generally or more colloquially. So at this temperature here, you have a mixture of water and steam, and you're going to add heat to that substance until all of the water has vaporized and converted into water vapor or steam. So you're going to have a constant temperature process to boil the substance. And then finally, the last phase is once we get up to once we've converted all of the water into steam, if we continue to add heat, it can warm up further. So the water vapor, the gas phase water, can warm up further, and you can go as high in temperature as you want until you've stopped adding heat. So at this stage, you have all gas phase water, or steam as it's called, and you're going to continue raising the temperature. So there's sort of the key concept here is that when you undergo a phase change is a constant temperature process. You're going to do the phase change at that temperature, and you're going to keep adding heat until all of the material has converted, and the amount of heat that you add is dependent on the phase change enthalpy of that substance, the fusion enthalpy or the vaporization enthalpy for this one. And then for the rest of these, where you just have a single phase, ice, which is solid, water, which is liquid, steam, which is gas, as you heat the substance, the temperature is going to increase and the amount of heat will be given by MC delta T. Now, the thing to also realize, which we'll see in the next problem that we're going to do here, is that each of these phases, so MC delta T, C is the specific heat capacity part, each of the phases has a different specific heat capacity. So for liquid water, it's going to be 4.184 joules per gram degree Celsius, the number that we use all the time in chapter 7. Ice, though, has a different heat capacity, and so does steam. So we're going to use different heat capacities for each of these segments here. But for all of those where we're just raising the temperature, that's how we calculate heat, MC delta T. All right, so let's go through that with a problem. This one's going to have all of these steps involved. So this is basically as complicated as it can get. The ones you'll do on homework assignments and tests will likely not be this complicated, but here we're going to do, again, all different processes. So this is going to kind of approximate what I just graphed out for you, which is we're starting with 5 grams of ice, and it's at minus 20 degrees Celsius, and then we're going to heat it all the way until it's gone to the gas phase, and then the temperature of that steam or that gas phase water is up to 140 degrees Celsius. So we want to know how much heat is absorbed, how much total heat does it require to go through this whole process. And so the way that you want to approach a problem like this is you want to take it in different stages, where each stage is either warming the substance until the phase change temperature or then changing the phase of that substance. You're going to calculate each of those individually and then add them up at the end. So when you have a process like this that has a few different stages involved of heating, you can calculate the heat for each stage and then add them up. They're all additive at the end of this, okay? So the first thing we're going to need is, for some of these stages, we are going to need the moles of water, but let's go through all the different stages first. All right, so stage 1, which again is going to be represented here with this blue line. I'll try to do these in the same color as the previous slide so you can kind of see the correlation. So stage 1 is heating up the ice from minus 20 degrees to 0 degrees. So you're starting out with solid water or ice. It's at minus 20 degrees Celsius, and you're going to heat it up until you get to the next phase change temperature, which is 0 degrees Celsius for water. Now, again, the temperature that these phase changes occurs depends on what substance it is. For water, you guys should know that it melts at 0 and boils at 100. That's common knowledge for the most part. But for other substances, these temperatures will be different. But for water, we're going to warm it up to 0, and that's when it'll start melting. So the heat for this first stage, for any stage where we're just warming up a single phase, is going to be MC delta T. We just have to make sure that we use the right specific heat capacity this time for the solid, because we're in the solid phase at this temperature. So we have 5 grams of ice, and we gave you here 3 different specific heat capacity values. As I said, they're all going to be different from each other. So solid water has a lower specific heat capacity than liquid water, and so we're going to use 2.09 joules per gram degree Celsius or gram Kelvin. And then the temperature change in this phase, minus 20 to 0, is a delta T of 20 degrees Celsius. We're raising the temperature by 20 degrees Celsius. So that's the delta T that we'll use. And so that comes out to 209 joules. And I didn't specify which unit to do the answer in, but we're going to end up doing it in kilojoules because it's going to be a lot of joules. So that's the difference in temperature. So we're warming it up from -20, which is where we're starting, up to 0 degrees, which is the temperature at which it'll start melting.
Right.
And so in that range, you're warming it 20 degrees. So that's the delta T that you'll use. Yeah? Well, you can use, remember it's a delta T, so Kelvin and Celsius are the same. So if it was Kelvin, it would be from 253 to 273 Kelvin, which is still a difference of 20 degrees. So whichever delta T you use, you'll get the same number. So again, keep those things straight when we're using absolute temperature versus delta T. That's when the units can matter or not. All right, so that's going to be the amount of heat, 0.209 kilojoules, required to warm the ice from -20 to 0. Then, as we said, once we get to 0 degrees Celsius, shown in red here, we're going to melt the ice to water. And so that's going to be a constant temperature process. So stage 2 is going to be melting the ice. And so for any phase change, we're going to just use the phase change enthalpy. Now these phase change enthalpies, fusion and vaporization, those are going to be per mole of substance. So for this step, we need to calculate the moles of water and then multiply it by the enthalpy of fusion to figure out how much heat is required to melt that much water. All right, so the heat for these processes, there's no temperature term, it's a constant temperature process, but we're going to take the moles of the water, or the ice in this case is still in that form, and multiply it by the appropriate phase change enthalpy, which for melting is going to be the fusion enthalpy. All right, so we're going to take those two and multiply them together. So we need to calculate moles of ice because we didn't give that to you, but again, moles is just mass divided by molar mass. So we have 5 grams of water, which whatever form it's in, is going to have a molar mass of 18.02. So we have 0.278 moles. All right, so the phase change enthalpies are typically going to be per mole of substance. They could be per gram as well, so you have to look at the units that we give you. But more often they're going to be per mole, so we're going to use moles of substance, 0.278. And we're going to multiply that by the enthalpy of fusion, which is 6.02 kilojoules per mole. And again, paying close attention to units, because some of these are in joules, some are in kilojoules, so we have to make sure we're keeping that straight as well. But when we multiply moles of substance by the enthalpy of fusion, that's going to tell us how much heat is required to melt that amount of substance, which is 1.67 kilojoules. So that's going to be the heat required to melt this ice once we get to 0 degrees Celsius. So we have 2 of those stages down now, color-coded as I showed in the previous diagram. All right, so once we melt the ice, now it's all in liquid form. And now we're going to heat up the liquid to the next phase change temperature, which is 100 degrees Celsius. So here we've gotten all liquid water once we melted it all, and we're going to warm it up to the next phase change, which is 100 degrees Celsius. So I'll do that in green just like I did above. All right, and so stage 3 of this, which is shown in green on the previous, spell it correctly. Stage 3, we're going to warm the water, the liquid water now, from 0 degrees Celsius where it's melted up to the next phase change temperature, which is 100 degrees Celsius. All right, and again, whenever we're warming up a substance that's a single phase, we're going to just use MC delta T, but we have to make sure, again, we use the right heat capacity for this. So in this phase here, we still have 5 grams of substance. Now we're going to use the more typical heat capacity for water that we know. The heat capacity for liquid water is 4.18. That's the one we used all the time in chapter 7, because we were only dealing with liquid water in that chapter. And the delta T for this phase, 0 to 100 degrees Celsius, is 100 degrees Celsius. So that's going to be 2,090 joules.
What does that stage you say? Like, what's that here to see?
Liquid, LIQ. So that's we have to make sure we use the correct specific heat capacity for the liquid in this case, because we're talking about liquid water. So this heat is 2.09 kilojoules to warm the water from 0 to 100. So that's stage 3. And then after we get to 100 degrees Celsius, then we're going to boil it, because we're going all the way up to 140, so we're not stopping yet. We're going to boil the substance. I showed that, I believe, in black. So when you boil the substance at 100 degrees Celsius, again, whenever we're doing a phase change, we're going to just use the phase change enthalpy to calculate how much heat that is. One of these days I'll spell it right. So stage 4, shown in black on the previous slide, and also here, is going to be the boil the water. And so for a phase change, the heat is just going to be the moles of the substance times the appropriate enthalpy. If we're talking about boiling, it's going to be the enthalpy of vaporization, delta H VAP, as it's abbreviated. And so we need to multiply those two numbers together. We calculated moles of substance earlier as 0.278. We're not changing the amount of substance during this process. And then the enthalpy of vaporization is 40.7 kilojoules per mole. And so the total amount of heat required to vaporize the substance is 11.3 when we multiply those two together. And that's again in kilojoules. Now, one thing you might notice, and maybe you should think about, and I'll kind of tell you why it is, but you should also see if it makes sense to you individually. You notice that the enthalpy of vaporization, 40.7, is quite a bit larger than the enthalpy of fusion, which is 6.02. It's over 6 times larger. So the question is, why is that? Well, remember what's happening in these processes. So when you want to melt a substance, you have intermolecular forces that are holding it together in a solid, and you have to break some of those to make it a liquid. But remember that the molecules are still in contact in the liquid, so a lot of those intermolecular forces are still intact. But then when you want to boil a substance, you have to break all of the intermolecular forces. So to go from liquid to gas, you have to break all the IMFs and separate them completely. So in just about every substance that I can think of, the enthalpy of vaporization is significantly larger than the enthalpy of fusion, because to vaporize, you have to break all of the intermolecular forces. Yeah?
For stage 2, why did you use the delta H?
Because we're melting the substance at that point. So each phase change has a specific enthalpy associated with it. Melting or freezing is going to be the fusion enthalpy, and then boiling is going to be vaporization. So there's 2 different enthalpy changes associated with each of those phase changes. And then the last stage, which I showed in magenta, is going to be where we're heating up the gas phase of water or the steam up to the final temperature of 140. So again, now we're in a single phase after we've boiled it all. And so stage 5 is going to be just warming up the gas phase water from the temperature at which it was formed, which is 100 degrees Celsius, to the final temperature, which was specified here as 140 in this problem. So for this stage, it's going to be MC delta T again, but this time we have to use, again, this is still the mass of the gas, but we have to use the heat capacity of the gas phase now times delta T. So same mass, 5.00 grams. And then the heat capacity for gas phase water is 2.00, so you have to make sure we use the correct specific heat capacity for each phase. So that's 2.00 joules per gram degrees Celsius. And the delta T for this phase, we're going from 100 to 140, and that's where we tell you to stop in this problem. So delta T is going to be 40 C or 40 K. And so that amount of heat is 400 joules, which is 0.400 kilojoules. All right, and I gave myself a little bit of extra space here because these do take up a lot of room for doing all 5 phases like this. Again, this is more complicated than you'll likely see in a homework or test, but this is basically the complete picture here. So finally, what we have to do is to get the total amount of heat, we just have to add all of those together. All right, so there's 5 stages, each we calculated heat for. So it's going to be 0.209 kilojoules plus 1.67 plus 2.09 plus 11.3 plus 0.4. So all those numbers added together that we just calculated for each individual stage of this process. And so that comes out to 15.7 kilojoules. So that's the total amount of heat needed to take this 5-gram chunk of ice, warm it all the way up, boil the water, and then warm up the steam up to 140. So that's how much heat required. Now you do notice though that most of that heat, 11 out of 15 or so kilojoules, comes just from boiling it. So boiling a substance does require a lot of energy because you have to break all the intermolecular forces. The rest of these, of course, depend on the specific heat capacity and all that, but most of the heat involved is going to be just for boiling it. All right, any questions on that problem or that basic idea? All right, we'll do one more like this, but just a little bit less complicated this time. Or no, I don't have another one, so that's it. I guess I took that out. But anyway, this is, as I said, as complicated as it gets. In most problems you'll do along these lines, it'll be maybe just 2 or maybe 3 phases. So we did all 5 here, but you'll have ones like this that are a little bit less complicated, yeah?
Problems right there. You didn't actually give yourself more space.
Oh, I didn't? Shoot. Yo. Sorry. Yeah, it is a different problem. I inserted a blank page here, and then it didn't show up in the most... Okay. Crap. All right. Thank you for pointing that out. There is another problem here. I'm just spacing out. And now I think I froze this. Oh, come on. The tablet doesn't like when I do a lot of erasing. So now I might be in a heap of trouble here. Yeah, let's actually do this problem. Let's not skip it. Thank you for not letting me space out on this. All right, let me put it up here at the top. I meant to give myself more space. So anyway, the total heat is, again, just the sum of all of those. I should have room to do this one. This next problem here is not nearly as complicated. All right, 15.7 kilojoules, that's the answer to the one above. I'll draw a line below that so you know that that's the end of the previous problem. All right, now we're gonna do one more. Here, it is here. I just thought I took it out for a second. And this time we're gonna be a little bit less complicated, as I said. So we're gonna take ethanol, which is a different liquid substance, which is found in adult beverages, among other things, and gasoline. And from the data below, calculate the total heat when we have 0.333 moles of ethanol and it's cooled to liquid ethanol. So we're starting with vapor at 300 degrees Celsius and we're cooling it down to a liquid at room temperature 25. So we'll notice here that the boiling point is 78.5 degrees Celsius. So above that temperature it's going to be vapor, and that's where we're starting. We're starting at 300. And then below this temperature is going to be liquid, so we're cooling it below the boiling point. So let's think about the different phases that are involved here. So the first stage is going to be, we're going to cool the vapor. So we're starting with vapor at 300 degrees Celsius. And that will cool down until we get to the boiling point. So the boiling point of ethanol is 78.5. All right. So we're going to cool the vapor from 300 to 78.5, which is where it'll start condensing. Now here we're going in the opposite direction. Before we were starting with solid and we were heating it up. Here we're starting with gas phase substance and cooling it down. So we're going in the opposite direction. So the signs are going to be different. They're all going to be negative in this case, but the math is still very similar. So the first stage is going to be to cool the vapor down from where it starts to where it's going to undergo its first phase change, which will be the boiling point of 78.5. So when we're cooling down a single phase, it's MC delta T. And we just have to make sure that we use the correct heat capacity for the gas phase, because that's where we are now. So we have to figure out how many grams of this substance we have. So 0.333, I didn't give you the chemical formula for that, did I? I should have.
Why is it like the 300 degrees Celsius is 78.5 degrees Celsius instead of 25 degrees Celsius?
Sorry, what is the question?
Oh, so like this is step 1, cool the vapor from 300 degrees Celsius to 78.5 degrees Celsius.
Yes.
Right?
And that's because the boiling point is 78.5.
Oh, okay.
So that's where we're going to cool it down to. So once you cool it to the boiling point, that's when it's going to start condensing. So we're going in the opposite direction this time, but at the boiling point, that's where the liquid and vapor will interconvert. Now, we need the grams of ethanol in this case, which I think I forgot to give you. So I gave you moles. I didn't give you the formula for ethanol. So ethanol is, so it's going to be C2 H6O. So that I should have given you. I'm sorry about that too. This is a poorly set up problem. But anyway, the grams of ethanol, we have 0.333 moles. And the molar mass for ethanol is, I think, 46 or so. Again, I didn't give you the exact formula, and I'm not going to spend time on that, but it's 15.3 grams. All right, so that should have been more easy for you to find. But again, we might give you moles, we might give you grams, and in most cases you'll need both, but you'll need the molar mass to do that, which I didn't give you here. All right, so with that out of the way, let's calculate heat for the first stage. So we need the mass of ethanol, which is 15.3 grams, not directly given to you, but you'll need that if you're going to use specific heat capacities. And then we use the specific heat capacity of the gas phase substance, which is 1.43. Here we're looking for heat in joules, so we're not going to convert anything for this step. And then the delta T, here we're going, final temperature is 78.5. Initial temperature is 300. And so this comes out to a negative number, negative 4,859 joules. So we do need to make sure we get the signs right in these. We'll do it in joules and kilojoules just to see. I think kilojoules ends up being better also. All right, so anyway, we need to make sure the signs are correct though, because here we're cooling the substance down, so heat's going to be negative whenever you're cooling something down. So again, the equation tells us that if delta T is negative, Q is also negative. And then step 2, we're going to be condensing the vapor. So as I said, we're going to cool it down to the boiling point, and then at that step, it's going to start condensing back into a liquid phase. So once you get below the boiling point, it'll be condensed into the liquid. So we're going to condense the vapor phase that's initially present. And so again, when we're doing a phase change, the heat is going to be the moles of substance usually times the delta H of that process. Now the difference here though is that here we're giving you the enthalpy of vaporization, which is this number there, but here we're not vaporizing the substance, we're condensing it. So remember that when we're going in the opposite direction from liquid to gas, we have to change the sign of delta H. So it's going to be the moles of substance times the negative delta H of vaporization, because here we're condensing, not vaporizing. So again, that's where the signs are going to be crucial. So it's going to be 0.333 moles, and then negative delta H of vaporization is minus 40.5. And that's going to be minus 13.5 kilojoules, or minus 13,500 joules. Kilojoules is probably better here, but I think I asked for joules, so we'll do both. So it's negative because we're condensing the substance. So when you have a delta H of vaporization, that refers to the enthalpy change for converting the liquid into the gas. Here we're going opposite, gas to liquid. So as we talked about in chapter 7, when you flip the direction of a chemical or physical process, you flip the sign of the delta H that's associated with it. So when you're going from gas to liquid, you need to switch the sign of the vaporization enthalpy from positive to negative. And here we're cooling the substance down, so all the heat terms should be negative as you're going from higher temperature to lower temperature. And then finally, stage 3 is going to be to cool that liquid. So at 78.5, we've converted it all to liquid. And we're telling you in the problem that you're cooling it down to 25 Celsius. That's where we're going to stop. All right, and I didn't give you the freezing point of ethanol, but the freezing point of ethanol is like minus 40 or minus 50. It's pretty low. So you're not going to freeze the substance at this temperature. It's just going to be cooled down to 25 degrees Celsius. And that's where we stop. So that's going to be the last step. And again, when we're cooling a substance in a single phase, it's going to be MC delta T, and we just have to make sure we use the correct specific heat capacity for the liquid. So we said the mass of the substance is 15.3. Heat capacity for the liquid is given here as 2.45. So we have to use that value for this step. And then delta T is going to be 25 degrees Celsius is the final temperature, and then 78.5 is the initial temperature, so that's what, minus 53.5. But it's negative again, so it comes out to minus 2,005 joules, which would be in kilojoules rounded to 3 significant figures, minus 2.1. All right, and so then the total heat here in kilojoules would be minus 4.86 for the first stage that we got. So now we're just going to add them all together. Minus 13.5 for the second stage. Again, all negative because we're cooling the substance down. And then the last stage we found was minus 2.01. So the heat for this process is minus 20.4 kilojoules, which is if you minus 20,400 joules if you want it in that unit. But either of those would be correct. I think I asked for joules here, but those are both numerically correct. All right, so this time it's negative because we're cooling the substance down. And so that's an important difference here, is that depending on the direction that you're going, whether you're heating it or cooling it, you're going to have different signs for your heat. So this is an exothermic process, and as you know, if you condense steam onto something, ideally not your hand, but if you've done it before, you know what it feels like. That substance is going to transfer heat to the surroundings, which would be you in that case, and that doesn't feel so good. So it's a negative Q anytime we're dealing with cooling a substance down. All right, so any questions on heating curves? There's really just two ways to calculate heat for these processes, either a phase change or a temperature change, and you just have to use them both in combination with each other, and that, of course, depends on what situation you're talking about. So any questions on that? All right, the last thing we're going to deal with regarding heating and cooling a substance is going to be what's called superheating and supercooling. And so this is just a situation that occurs sometimes. There's not really anything quantitative you can easily say about it, but just we're going to introduce the concept and a little bit about why it occurs. So what happens in supercooling is a liquid is cooled below its freezing point. Now, one thing you'll learn in Chem 2, it's not really considered supercooling, but you can cool a liquid below its freezing point if it has something dissolved in it, and that's the concept behind how, you use salt on the roads to prevent them from icing up in the winter, which occasionally happens here. But that's a little bit different, because in that case, you're mixing two substances together. But even if you have a pure substance, just pure water, let's say, depending on how fast you cool it, depending on what kind of containers and all these different things, sometimes you'll cool it down. It'll get below 0 degrees Celsius and it won't be a solid. It'll be a supercooled liquid, meaning a liquid that exists below the freezing point. And so that can happen. Usually it's a sort of a temporary state. It doesn't usually stay in a supercooled state for very long. Actually, I know someone pretty well who studies supercooling. So my twin brother studies insects, and he studies their ability to supercool the liquid inside of their bodies to prevent freezing. So it's actually relevant to some biology and physiology stuff too. But nonetheless, that's the definition we're going to take for it. Now, why does it occur? Again, it's kind of complicated. We're not going to talk about the precise details of all of this. But what happens is sometimes it takes a period of time for the molecules to organize into a solid. So we're going to talk in the second half of Chapter 9 about more details about the structures of solids and how the atoms or the molecules that make them up will often organize into these regular patterns. And sometimes it just takes a period of time for that to happen. It doesn't happen instantaneously. So even though you've cooled the liquid below 0 degrees Celsius, the molecules just haven't had enough time to organize themselves into a solid yet, and so they stay liquid even though they're below the actual freezing point. So that's what supercooling is, cooling the liquid below the freezing point, but for some period of time anyway, it doesn't freeze immediately. And then superheating is the opposite. This is when a liquid is heated above the boiling point, and it doesn't start boiling quite yet. I would say this is probably a less common situation, but it can happen, at least temporarily, as we said. These are all sort of, temporary or what you call fleeting phenomena. They don't really typically persist for long periods of time, but they can appear in certain situations. And the reason why a liquid would be superheated is a couple things. You could have, uneven heating, because in order for a liquid to boil, when you see a pot of boiling water, what's happening is that the bubbles of the vapor, which are forming at that temperature, have to escape from the surface of the liquid. And so if you're heating the liquid unevenly, there might be parts of the liquid that are hot enough to boil, but it's not close enough to the surface for those water vapor bubbles to escape. That can be one thing. And then also, as we know, all liquids have surface tension. So you sometimes have to go a little bit above the boiling temperature to start the boiling process, because as those vapor bubbles approach the surface, they encounter the surface tension of the water and they don't immediately escape. So those are just, again, just very broad, very basic definitions of those processes. We don't want to talk about them in a lot of detail, but just to be aware that, in an ideal sense, when you get to the freezing point or the boiling point, the phase change will occur, but it doesn't always happen right away. And sometimes you can go on either side of those phase change temperatures and not have the phase change occurring immediately. And that's what we refer to as supercooling or superheating. All right, so any questions on that? This is kind of the last sort of phase change topic we'll cover at this level. So what we're going to finish with in this part of the chapter, and which again will be the last thing we'll talk about for this exam in this first half of chapter 9, are going to be what are called phase diagrams. So this is still dealing with phase changes, but this is basically a way of diagramming all the phases that can exist for a substance and what temperatures and what pressures they will exist at. So the basic definition is that it's a temperature-pressure diagram. So those are your two axes, temperature and pressure. And it's for a specific substance. Now you can have phase diagrams. We're only going to talk about those for pure substances in this course, just a single substance. You can also have phase diagrams for mixtures of substances, which is something you'll see in Chem 2 at the very beginning. But we're going to talk about just a pure substance phase diagram. So it's a temperature-pressure diagram. And why it's going to be useful is that it shows all the conditions of temperature and pressure under which it exists in its different phases. So at minimum, every substance is going to have three phases, solid, liquid, and gas. And so you'll be able to tell which temperatures and pressures does it exist as a solid, which temperatures and pressures does it exist as a liquid, and a gas, and so on. All right, so it's a temperature pressure diagram, and you can use it to figure out when a substance is going to be in which phase that it exists in. So the axes are pressure and temperature. You could, in theory, you could plot it in either way. It would give you the same information, but conventionally, the y-axis is pressure, and the x-axis is temperature. And so what a phase diagram is going to have is going to have lines that divide out the different phases. So you'll have a solid portion of the diagram, a liquid portion, and a gas portion at minimum, and then you're going to have lines in between them that show where those two will convert between each other. So you're going to have at least three regions, solid, liquid, and gas. But sometimes you'll have more than three regions because sometimes there's multiple solid phases. We haven't quite talked about that yet. We will maybe a little bit in the second half of this chapter. But some substances have multiple solid forms, basically. They're not just a single solid form. And the one that you should be familiar with from your everyday life is carbon. So carbon, the most stable form of carbon, we'll see the phase diagram for carbon in a little bit, but the most stable form of carbon is graphite, which is that sort of black, soft substance that used to be used in pencils. And then pure carbon can also exist as diamond, which of course looks a lot different than graphite. So both of those are forms of carbon. So as we'll see in the phase diagram for carbon, you have two different regions for those two different solid forms. So you can have more than three regions, and that's typically going to occur when the solid form of that substance has multiple phases possible, which can be true for certain things. And again, we talked a little bit about this already. Why are they useful? They're useful because you can predict conditions at which phase changes will occur. You can predict vapor pressures of substances at different temperatures. Again, we have an equation for that, but the diagram allows you to do that more simply. And you can predict other properties, as we'll get into, and see all the different ways as we go through example problems how we can use phase diagrams to our advantage. And they cover a wide range of conditions. So it's, even sometimes conditions that don't exist normally on planet Earth, but very harsh conditions in some cases, and so on. And the other reason they're useful, which is not really relevant to this course, but when you do, synthetic chemistry, which is the part of chemistry where you're trying to make substances, you can often use the phase diagram for those substances to predict how would I make this substance? What temperature, what pressure do I have to go to for that substance to form? And so phase diagrams are very useful for that as well. So one of the simplest phase diagrams, and the one we'll talk about first, is water. All right, so let's talk about the different features in this phase diagram for water. So first we can identify the different regions of the diagram that are shown here. So typically, and now that we've talked about the different phases, this should make sense. So in this diagram we have temperature on the horizontal axis and pressure vertical. So if we go to lowest temperature, furthest to the left, and highest pressure, that would be the solid part of the diagram. All right, because we know if we cool the substance down at the lowest temperatures we get to, it's gonna exist as a solid. So all the way on the left is solid, and then as we heat it left to right, going from increasing temperature, we'll have the liquid be the middle part of the diagram, and then gas will be over here. Okay, so those are the three regions. Solid is going to be the lowest temperatures and also typically highest pressures. Gas is going to be the highest temperatures and lowest pressures, so it'll be the bottom right of the diagram, and then liquid will be in the middle. So those are the three regions, and most phase diagrams look qualitatively similar to this. Now, of course, where these dividing lines occur depends on the substance that you're talking about, but you're going to have those three regions typically in any phase diagram, or at least those three. So let's talk about some of the features of this diagram that we have. So here's the dividing line between solid and liquid. This line here is called our solid liquid line. It divides those two phases. So this allows us to predict the melting point at different pressures. All right, because everywhere along this line, this is going to be the temperature at which the solid and liquid interconvert, and as we go up the line, we're going to higher and higher pressures. And you can see it changes a little bit. This line is not perfectly vertical, so that means the melting point does depend a little bit on pressure, but not a huge amount. But anywhere that we are on this line here, it tells us at which temperature we would convert from solid to liquid, which we know at atmospheric pressure is going to be 0 degrees Celsius for water. Now the other line that we have here divides liquid and gas from each other. So I'll draw that in green here. And this again is the borderline between liquid and gas, so that allows us to predict the boiling point at different pressures, which you can see in this case is much more strongly dependent. All right, and where those phase change lines intersect normal atmospheric pressure, 760 millimeters, that's going to be the normal melting and the normal boiling point of that substance. So if we go over at normal atmospheric pressure 760, which is shown here on this diagram, draw a horizontal line over, this point here, which is not marked, but I'll label it there as point A, that's going to be the normal melting point. Because that's the temperature at which the solid and liquid interconvert at 760 millimeters of mercury, normal atmospheric pressure. And you can see if we extrapolate down to the x-axis, that's going to be 0 degrees Celsius, as we would expect for water. And then here, this point was shown as a little open circle, and I'll highlight it here and label it as point B. That's going to be our normal boiling point, which again is the liquid gas borderline at atmospheric pressure, normal atmospheric pressure. And that occurs, as we expect, at 100 degrees Celsius. Okay, so that gives you some information about how you can use the phase diagram to predict phase change temperatures and which pressures and which temperatures each of those three phases, solid, liquid, gas, would exist at. So that's how it works for water. So let's look at that a little bit more and talk about some additional insights that we can get from this. So again, at a very basic level, we just have solid, liquid, and gas regions, and we can predict how they are arranged in this diagram pretty easily, but there's some other insights that we can gain from this. Now, one thing you'll notice if you look closely is that this solid liquid line has a negative slope to it. It's sloping a little bit from bottom right to top left. So let's think about what that means here. So let's say we start in this, it's kind of hard to do in this diagram because this line is not very, very slanted, but let's say we start here at that point. And then let's say we increase the pressure of the substance. So we're starting here where it's a solid. We increase the pressure, and eventually we're going to cross over and it's going to be a liquid. I didn't draw that perfectly, but because the line is slanted, as you increase the pressure, you'll go from solid to liquid because of the way the line is slanted in the negative direction. So what this means is if you have a negative slope for your solid liquid line, when we increase the pressure, it converts from a solid to a liquid. And so what that means, little 3 dots meaning therefore, in this substance, which is water, the liquid is more dense than the solid. Because when we increase the pressure, we're basically compressing, forcing the substance to be more compact. And as we do that, it converts from liquid to solid, telling us from solid to liquid, telling us that it's the liquid phase that is more dense. So if we increase the pressure and it converts from solid to liquid, that means liquid is more dense than solid. And that's actually not the most common situation, but for water it's true. We know that if you have a glass of ice water, the ice cubes float on top of the water. And that's because ice is less dense than water. In most substances, the solid is more dense, it's more compact, but in water that's not true. So the slope of this solid liquid line can tell you which of those phases is more dense, the solid or the liquid. So as you raise the pressure, you're increasing the density of the substance by basically forcing it to be more compact. And as you raise the pressure in this case, it'll cross over that line and go from solid to liquid. All right, so that's what the negative slope of that tells us. Now there's another point in this diagram which we haven't labeled yet, but it's right here where all 3 of the lines intersect, and I'll call that point X. So that's called the triple point of this diagram. And this is going to be the point at which all 3 phases can coexist. So solid, liquid, and gas are all present at that triple point. Now you'll see that that's way below atmospheric pressure. So on normal surface of the Earth, you're not going to have a pressure where all 3 of those are, or a temperature at which all 3 of those are together. But at that lower pressure, that's possible. And what it also means is that under those conditions, which for water is shown as 4.579 millimeters of mercury and close to 0 degrees Celsius, but under those conditions, all 3 of the phases have the same vapor pressure. Well, the solid and liquid, I should say. The solid and liquid have the same vapor pressure. All right, but that's called the triple point. The most important thing is that you can identify that on the phase diagram as the intersection between all 3 of those lines that divide those 3 phases, where they all come together there. And then another point on the diagram is you'll notice that the liquid gas line kind of just ends. And that's not because we just decided to stop drawing the diagram. At some point, the dividing line between liquid and gas really does come to an end. And I'll call that label here as point Y on the diagram, and that's called the critical point. So when you get to the critical point, this is going to be the point at which the vapor can no longer be liquefied. So if you go beyond this temperature and pressure here, further up and to the right, at that point you can no longer liquefy the vapor anymore. So beyond this point, you don't really have separate liquid and vapor phases. Beyond this point, you have what's called a supercritical fluid, and they're kind of indistinguishable from each other. There's no clear distinction between liquid and vapor at this point. I'll call it gas phases just to be more consistent with the diagram. But anyway, the liquid and gas phases beyond the critical point are indistinguishable. And they exist as what's called a supercritical fluid. spell it right, fluid. All right, so supercritical fluid is what it's going to be called once you've gotten beyond the critical point. You don't have separate liquid and gas phases anymore. You just have a single phase that's in some level indistinguishable between the two. So there is research going on supercritical fluids. Like, for example, carbon dioxide can be converted to a supercritical fluid at pretty reasonable temperatures and pressures, and people are studying the behavior of that because it has some properties that are distinct from both the liquid and the gas phases. It's almost like a new phase, but in reality, it's just a fluid phase that's no longer distinguishable between liquid and gas. All right, so that's kind of some other things you can get from a phase diagram. We're going to look at a couple more here just to see some different features that you can have. So in this diagram for CO2, what you'll notice is that we still have the same three regions: solid at the left, liquid in the middle, gas on the right. But if we're here at 1 bar, which is basically 1 atmosphere, for this is carbon dioxide for the phase diagram, should be subscripted, CO2. So carbon dioxide here. As we go at 1 atmosphere, we start in solid CO2, and as we go and increase the temperature at that constant pressure, we're going to convert directly from solid to gas. So that's a new phase change that we haven't introduced yet, where you go directly from solid to gas. So as we increase the temperature here, anywhere below the triple point here, but if we're at 1 atmosphere, 1 bar at this level here, as we go left to right raising the temperature, we start out as solid and we go directly to gas. We don't pass through the liquid phase. So that process is called sublimation. That's another type of phase change we can sometimes have. And you've probably seen dry ice before, so dry ice is just solid carbon dioxide. So when you have solid carbon dioxide, which we call dry ice, if you let it warm up, it doesn't turn into a liquid, it just goes straight into the gas phase carbon dioxide. And so that process of converting straight from solid to gas is called sublimation. So for CO2 at 1 atmosphere, we can predict the temperature at which it sublimes, because that's going to be the temperature at which we get to that borderline between solid and gas, which occurs at minus 78.5 degrees Celsius. So that'd be the temperature at which dry ice would start to convert into gaseous CO2. So when you have a dividing line between solid and gas phase, that's your sublimation line, and that process of converting is called sublimation as well. All right. So it only occurs at pressures below the triple point. But for CO2, the triple point pressure is pretty high. So for CO2, even at normal atmospheric pressure, you would have sublimation. For most substances, you have to lower the pressure well below atmospheric pressure to sublime them. That's what we would have seen in water there. And the other thing that we notice in this diagram here, which is a little bit different than water, is that in this case, we have a positive slope for the solid liquid line. So if we start here in the liquid phase and we raise the pressure, we're going to cross over to solid. And so that tells us that we have a more dense solid phase, which is actually the more common situation, but different than water. So this one has a positive slope, which tells us that the solid is more dense than the liquid for this substance. All right, so as we raise the pressure, that's going to increase the density of the substance, and as we increase the density of the substance, it converts from a liquid to a solid, telling us that the solid has the higher density between those two. So those are some additional things you can see from CO2 that are a little bit different than water, again, sublimation being the big one. And then the last phase diagram I'll show you before doing a bunch of example problems, which we'll probably have to finish next time, is, as I talked about before, the phase diagram for carbon, which has now 4 different regions instead of just 3. So gas is still highest temperature, lowest pressure, and then liquid would be over here. So these ones wouldn't be as easy for you to label off the top of your head, but so they'll typically be labeled for you. But again, because carbon has 2 different solid forms, it has 2 different regions on the left side of the diagram here at lowest temperature. And so the bottom one is graphite, and then the top one is diamond. So what you'll actually notice, there's a couple of things here. First of all, in order for diamonds to form, you need really high pressures because the dividing line between graphite and diamond occurs at 10 to the 9th Pascal. The normal atmospheric pressure is about 10 to the 5th Pascal. It's a weird unit for this diagram, but that's what I found. So, normal atmospheric pressure would be like somewhere down here. If this is like 10 to the 5th. So anyway, you have to go to really high pressures, about 10,000 times higher than atmospheric pressure to be able to convert graphite to diamond, but that can happen. So it is possible to make synthetic diamonds where you take, graphite and just pressurize it to ridiculously high pressures. But you have to go above 10 to the 9th Pascals. But that will convert graphite into diamond. And that's also how diamond forms naturally. It forms under very high pressures as well. And it's as you know, pretty rare, but it does happen. Now, the other thing that this diagram reveals is the false advertising that the diamond industry does to everyone, because you've probably seen the commercials where they say a diamond is forever. And that's not actually true because graphite is the more stable form of carbon at atmospheric pressure. So at some time period, if you have a diamond, it's going to convert to graphite because graphite is the stable form of that solid at regular pressure. So diamonds are not forever. Now in reality, it takes a really, really long time for that to happen. So on the normal human time scale, they are forever. But nonetheless, that's false advertising from a chemistry standpoint because diamond is not the most stable form, so it would not last forever here on Earth. Based on the phase diagram. But the important thing about this diagram is that it shows that in some diagrams you'll have multiple solid regions. This one has 2, but it can be more than 2 for certain types of substances as well. So they can be a little bit more complicated, but you'd still be able to make a lot of the same predictions that we've talked about. So with the remaining time that we have left, we might save some of these for next time just as a review. Let's go through and talk about just a bunch of different types of problems we can ask you. So now that you know how to read a phase diagram, let's just look at all the different things we can ask you about them that you might see on a homework assignment or an exam. So here we have a generic phase diagram, which it doesn't line up with water, but it has a very similar profile as water. And so one thing we could ask you is just asking which phases are present at different points in the diagram. So to do that, you have to be able to label the diagram, solid, liquid, and gas. Again, solid furthest to the left, liquid, gas furthest to the right, and liquid in between. And then it wants to know which phase is or are present at point A. So point A here is clearly in the solid part of the diagram, and it's not on the borderline between 2 phases. It's right in the solid region. So at that point, you only have solid. So that would be, probably a multiple choice question, for example. Which phases are present at point A? You would select solid only at that point because you're in the left side of the diagram and you're not on the borderline between any of the 2 phases. So that's one question we could ask you, just identifying, which phases are present. And then we could do the same thing here for a different point. What phases are present at point B? So again, you always want to start these by labeling the diagram. I guess that's a little bit hard for you guys to do because we give you the problems in Blackboard and you can't label the screen, unfortunately, but you have to keep straight which part of the diagram is which, and then you identify the point we're looking at. So at point B here, we're at the borderline between liquid and gas. So this would be at this point here, substance would be vaporizing or converting between liquid and gas. So whenever you're at a borderline between 2 phases, both of them would exist under those conditions. So at this temperature and pressure, which is about 200 Kelvin and around 1 atmosphere, a little bit less than 1 atmosphere, at that point, the liquid and the gas are both coexisting whenever you're on the borderline between 2 phases. So when you're on one of these phase change lines, that's another thing that it means. It means that both of those phases are present under those temperatures and pressures. So liquid and gas would be present at that point here, so that's another one we could ask. So here's a multiple choice question. Which temperature and pressure are closest to the triple point? So in this case, it helps to label them, but you don't really need to for this problem. Because the triple point, again, is the point at which all 3 of these lines intersect each other. So that's going to be that point there. So it wants to know, what temperature and pressure. So the triple point is a single point on the diagram where all 3 intersect, and it's going to be designated then by a specific temperature and pressure. So the pressure is very clearly 0.6 atmospheres if we go over to the y-axis. And then the temperature here is between 2, but it's between about 100 and 150, maybe a little bit closer to 100 Kelvin. And so it's going to be, in this case, choice A. The pressure is 0.6 atmospheres, so that actually eliminates all the rest. and the temperature would also be 120 Kelvin, so both of those work out, so it'd be choice A. So when you're identifying the triple point, you find the point where they all intersect, and then you just figure out the X and Y values that associate with that, which are the temperature and the pressure that the triple point would occur at. So any questions so far on those first 3 phase diagram problems? All right, let's just keep going through some more until we run out of time. So this one wants to know what are the normal melting and boiling points for this substance. So remember that normal means at 760 millimeters or 1 atmosphere. So those are the phase change temperatures at regular sea level atmospheric pressure. So to identify normal boiling points and melting points, we have to again keep straight which region of the diagram is which. And then we're going to consider phase changes that occur at 1 atmosphere. And we're talking about normal melting points and normal boiling points. All right. So the normal melting point is going to occur when at 1 atmosphere we change from solid to liquid. So the solid liquid line at 1 atmosphere occurs there, which I'll call point X. So that's going to be the melting point because that's the temperature at which we convert from solid to liquid at 1 atmosphere of pressure. We extrapolate down to the x-axis here. And that's, again, we have to estimate a little bit, but that's going to be basically 110 Kelvin, thereabouts. So it doesn't have a very precise temperature scale, but you can see that point X here, when we go down to the x-axis, has 110 Kelvin. And then for the boiling point, we need to find the liquid gas line, liquid vapor line. So again, we're following the 1 atmosphere pressure to do normal boiling point, and that liquid gas line occurs there at that pressure. So this is the liquid gas line here. We'll call that point Y just to label it more clearly. And so Y is the boiling point of the substance. And if we extrapolate this down to the x-axis, again, it's in between 2 temperatures, so you're going to have to roughly ballpark this, but it's going to be about 220 Kelvin for this substance. Between 200 and 250. Again, it's an estimate. If it was multiple choice, you just want to pick the one that's closest to that. So again, we extrapolate down from the liquid gas line to the x-axis to find the temperature at which liquid and gas interconvert, which would be the boiling point for that substance, and at 1 atmosphere, that's called the normal boiling point. All right, so any questions on that? So again, identifying these phase change lines allows you to predict temperatures for phase changes. How many more do I have? Probably too many, right? All right, I'll do a few of these next time. Yeah, we're not going to get through all of them. Let's just do one more probably, and then I'll let you guys go. All right, so here we want to know what is the sublimation temperature for this substance at 0.4 atmospheres. Sublimation, as we said, is converting directly from solid to gas. So if we go to 0.4 atmospheres of pressure, which is what we're asking about here, and we find where does the solid gas line intersect. So this is the solid gas line here. It intersects at that temperature. And that temperature lines up exactly with 100 Kelvin. So at 0.4 atmospheres, once we get to 100 Kelvin, we start out as a solid. When we cross that line, we're going to go straight to gas. Solid to gas is sublimation. So the sublimation temperature for this substance is 100 Kelvin. All right, we have about 3 of these left, but I'll save them for next time just as a review. Any last questions before I let you go? All right, so next week we'll just wrap this a little bit up, which is going to be on the exam just as review, and then we'll get into the second half of the chapter, which deals primarily with solids.
I think I have a test at the time, like April 23, 2 p.m. I'll be taking a test during that time because I'll have to watch the video on it.
Okay, that should work.
I have a question really fast. So you posted the letter grades. Do you think it's possible to raise yourself up a letter
Oh,
at
yeah.
this point?
It should be